All right, so picture this. It's the turn of the 20th century, and physicists are feeling pretty good. They're patting themselves on the back, thinking they've pretty much figured out the entire universe. But there were these little nagging problems, clues hidden in experiments that just didn't add up. And these little clues, they were about to blow everything we thought we knew wide open.
So here's the big one. This is the central mystery we're going to be digging into. And yeah, I know, it sounds like something straight out of a comic book, right? But believe me, this is the absolutely bizarre reality that scientists found themselves staring at. It's really the core idea of the entire quantum world. Okay, so where does a story like this even begin? Well, the first clue, the first piece of evidence that something was seriously wrong with the physics of the day, it came from something that sounds almost ridiculously simple. Seriously, all they did was shine a little light onto a piece of metal.
And this is the exact moment where the old physics just fell apart. See, the classical rulebook said light is a wave, so a brighter light should be a bigger wave, right? It should hit that metal with more oomph, knocking electrons out with way more energy. But that's not what happened. Not even close. Reality just wasn't playing by the rules anymore.
This whole puzzle, this crime scene, actually has a name. It's called the photoelectric effect. And for the physicists back then, it was a complete and total mystery. The old rules just couldn't explain it, which could only mean one thing. The old rules were wrong. And think about that for a second. If you're wrong about something as basic as light, what else are you wrong about? They needed a whole new theory, a whole new way of thinking.
And then comes the solution. And you've probably heard of the guy who figured it out. A young patent clerk named Albert Einstein. He had this wild idea. What if light isn't a continuous wave? What if instead it comes in little packets, like tiny little bullets of energy? He called them quanta. So brighter light didn't mean more powerful bullets, it just meant more of them. And just like that, with one brilliant, radical thought, the mystery was solved.
So, okay, the floodgates are open now. Light, which everyone thought was a wave, can also be a particle. But this just opened the door for an even crazier question. A French physicist, Louis de Broglie, thought, hang on a second, if a wave can act like a particle, what about the other way around? Could a particle act like a wave?
I mean, this was absolutely revolutionary. De Broglie suggested that everything, and I mean everything, from an electron to a baseball to you and me, has a wave-like nature. We're all, fundamentally, waves. Now, for something big like us, that wavelength is so incredibly tiny you could never ever notice it. But for a tiny little electron? Oh, for an electron, being a wave is pretty much its whole deal. And this whole particles are waves thing leads to maybe the weirdest consequence of all. Just think about it for a second. If you have a wave in the ocean, can you point to it and say it's right there? No, of course not. It's spread out. And that's the key. This spread outness of being a wave introduces a kind of fundamental fuzziness to the very nature of particles. So let's say you try to pin that electron down. You want to know its exact location, right? Right down to the nanometer. And you can. You can measure its position with incredible, incredible precision. But there's a catch. There's always a catch.
And that catch is, the more precisely you nail down its location, the less you know about where it's going. Its momentum, its speed and direction becomes a total blur. And it works the other way too. The better you know its momentum, the fuzzier its location gets. It's this fundamental trade-off that's built right into the universe. You just can't win.
And it's super important to get this. This isn't a problem with our measuring tools. It's not like if we just built a better ruler, we could solve it. No. The universe itself says you can't know both. A particle literally does not possess a perfectly sharp position and a perfectly sharp momentum at the same time. This fuzziness, this uncertainty, it's just part of the fabric of reality. All right, so let's recap. The old rule book, totally useless. We're now living in a universe that's fuzzy, based on probabilities, and just deeply, deeply weird. So obviously physicists needed a new set of rules. They needed a new quantum rulebook to even begin to describe this strange new world. And right at the heart of this new rulebook is something called the wave function. It's basically the main character of our story from here on out. You can think of it as the complete biography of a quantum particle. It holds every single piece of information you could ever know about it. But the kind of information it gives you is completely different from anything in the old physics. And here's the massive mental leap you have to take. The wave function isn't a wave of stuff, it's a wave of probability. It's a cloud of possibilities. It doesn't tell you where the particle is, it tells you where it might be. The particle isn't in any one spot until you actually go and look for it. Before you look, it's kind of everywhere and nowhere at once. So yeah, certainty is out the window. It's all about chance now.
So if everything is just a cloud of probability, how can you predict anything? Well, that's where this comes in, the famous Schrödinger equation. And don't worry, we are not doing math here. All you need to know is its job. Think of it like this. Newton's laws told you how a planet moves through space. Well, Schrödinger's equation tells you how that wave of probability moves and changes over time. It's the master equation for the quantum world.
And here's a neat little detail about these matter waves. They actually have two different speeds going on. You have the speed of the little individual ripples, but then you have the speed of the overall wave packet, the clump that we think of as the particle. It's that speed of the whole clump, the group velocity, that lines up with what we'd actually measure as the particle's speed. Kind of cool, right? Okay, so we have our new rulebook now, right? We've got the wave function, we've got Schrödinger's equation. Now we can start to see what this new physics actually predicts. And let me tell you, this is where things get truly bizarre. So buckle up. Let's do a little thought experiment. Imagine you could trap a single quantum particle inside a tiny, tiny box. Now, remember, that particle is also a wave. And just like a guitar string, only certain waves can fit perfectly inside that box. This has a huge consequence. The particle can't have just any old energy. It can only have specific, discrete energy levels. Its energy is quantized. But here's the kicker. The lowest possible energy level isn't zero. That means a trapped quantum particle can never be perfectly still. It's always jiggling around, even at its lowest energy state.
All right, time for the grand finale. And this might be the weirdest trick of them all. Imagine you roll a ball at a hill. If it doesn't have enough energy to get to the top, it's never going to get to the other side. That's just common sense, right? But what happens if that ball is a quantum particle?
Classically, in our everyday world, it's impossible. No way. The ball rolls back down. You can't just walk through a solid brick wall. End of discussion.
But quantum mechanically, yeah, it can happen. The particle can just appear on the other side of the barrier. Poof. Even though it never had enough energy to climb over it. It's literally like being a ghost and walking through a wall. This spooky ability has a name. It's called quantum tunneling. And I have to stress, this isn't just some weird theoretical quirk. It's real. It's happening all the time. It's a huge part of why the sun is able to shine. It's fundamental to how a lot of our modern electronics work. It's a real, measurable, and yeah, completely bizarre part of how our universe operates. So how in the world does that even work? Well, let's go back to our friend, the wave function, that cloud of probability. When that wave hits the barrier, sure, most of it gets reflected, but a little bit of that probability wave actually leaks through to the other side. This means there's a tiny but very real chance that when you go to measure the particle, you'll find it on the other side of the wall. It didn't break through it, it just sort of tunneled through the probabilities of reality itself. And that's really the heart of our quantum detective story. It all started with a simple observation about light hitting metal, and it led us to a whole new reality. A reality that runs on probability and uncertainty and a set of rules that just feel like they shouldn't be true. And it really makes you wonder, right? If all of this strangeness is the foundation of our everyday world, what else don't we know? What other secrets is the universe hiding from us?